Question 1. So this is a really important question you need for the exam. The name of it is the electron diffraction experiment. What's happening? Electrons are fired at a crystal or at a target. We could make reference to the de Broglie formula. The wavelength of the electrons is a similar size to the gap between the atoms. So diffraction takes place. What do we observe? We get this circular pattern on the screen, which is a fringe pattern, which shows constructive and destructive interference, which demonstrates that particles behave as waves. So, exam tip, include lots of detail. Always useful to make reference to a formula and use the correct terminology. And this is a bit of a synoptic type question because we're referring back to the work we did in waves, so fringe pattern, constructive, destructive interference, wavelength, and so on. Like we say, question 2 would be a fairly straightforward question in the exam. You might get something that's simple, but all we need to do is to select the correct formula and substitute the values, and we get the wavelength. In this case, it's going to be 1.21, 10 to the minus 10. And then we need to compare that to the spacing, same order of magnitude, 10 to the minus 10. So we're going to have wave behavior. We will get diffraction and possibly interference. Perhaps not surprisingly with the football. So again, we can calculate the wavelength. We've got a relatively large mass and large velocity, well, a relatively small velocity. But because we have this dominant Planck constant on the top, then we're going to get this very, very small wavelength. If we compare the wavelength to the gap, 0.8 meters, then it's much, much smaller. So no diffraction takes place and the football behaves as a particle. So a couple of points on this for exam tips. Always show you working, very, very important. Always make sure that you make a comment if required. So it says decide whether a wave or particle model should be applied. A typical loss mark in the exam would be students just calculating the wavelength and then not saying whether it's going to be a wave or a particle model. So make sure you answer the question and get that extra detail in. Okay, question 3, so a little bit more difficult. So I've given you the hints here. You wouldn't get those in the exam, obviously. And again, this is a bit synoptic because it's referring back to the work in the electricity topic. So we've got 5 kilovolts, 5,000 volts. What is the energy of each electron? So we're assuming that they're stationary to start with. They're accelerated through this PD of 5,000 volts. We can calculate the work done on the electrons, which will appear as the kinetic energy. So work done is Q times V. We know this from the electricity topic and also from the formula booklet. So all we need to do is to multiply the charge of one electron by the voltage and we get the energy. So this is going to be the energy gained, which will appear as kinetic energy. And again, you wouldn't get this hint in the exam, but we do need to know that the work done is when we have an energy transfer if a force moves a distance. So we have a transfer from electric potential energy into kinetic energy. So mathematically, fairly straightforward. Rearrange to make V the subject, use your previous value, and we've got the mass of the electron, and we can find the velocity. Expect a really high value, so 10 to the 7 sounds about right. If you're getting much lower values, then you've probably made a mistake, because normally electrons move extremely quickly. What is the wavelength? So we're going to use de Broglie. So we can put the numbers into the de Broglie formula, and we get 10 to the minus 11. And we might anticipate it's going to ask us about, does it behave as a wave or a particle? We know it's going to behave as a wave. Oh, it does, there we go, part D. So it says, what would happen if they were diffracted, or so if they were directed at a gap of 10 to the minus 11. So it's the same order as the wavelength. So the electrons will behave as waves, they will diffract and interfere, which is what we'd expect to see in this case. Exam tip for this question, always show your working, especially on multiple stage calculations, because if you make a mistake right at the start, you're going to carry that through all the way, and you will get error carried forward even for incorrect answers, only if you show your comprehensive working out. Right, more difficult questions. So if we increase the voltage, so perhaps not surprisingly, we're going to get a larger energy, a larger kinetic energy, which will appear as a larger velocity. And then we link it to the de Broglie formula. A larger velocity, we're divided by a bigger number, but the mass hasn't changed, h hasn't changed, so lambda is going to be a lower value. So then we need to think, okay, if it's a lower wavelength, how will that affect the fringe spacing? And we can make reference to the Young's fringe formula here. So we've got lambda is equal to A times y over d, and make y the subject, y is the fringe separation, is equal to lambda d over A. So the distance hasn't changed, the slit spacing or the gap hasn't changed. If we have a lower wavelength, then we're going to have a lower fringe spacing. So quite a difficult question, quite synoptic. It's bringing together lots of ideas, and in your answer, you would need to make reference to the formula. Finally, we've got why do we get circular fringes rather than a line, which is what you might expect, for example, with the Young's fringes or the diffraction grating. So this is a little bit more difficult, and the exam tip here would be to read around the subject, read your textbook, try some extension questions, look at the more complex questions whenever you get an opportunity, for example, with the Physics Olympiad, because this is a little bit more difficult. And to explain it, we need to think, well, what's going on just if we have two slits next to each other? So if we have two slits, we get a line of fringes because we only have one plane, one orientation of slits. But actually the way the carbon target is structured, so graphene consists of multiple layers of gaps, all at different orientations. So not just 4, but thousands and thousands of orientations. So we might have a horizontal orientation and a vertical, and then at another angle. So wherever we get these particular orientations of planes, we're going to get effectively a line of fringe spacing at that particular angle. So if we have multiple different planes, that's all the angles all the way around a circle, 360 degrees, we're going to superimpose these lines on top of each other, which will create effectively a circular pattern.